In this section, we're going to generalize the theories about matrix equation and their solution set, and we will see that the solution set from the vector subspace of R to the K. So let's first look at the following definition. So the null space of n by n matrix A is set of all solution to the homogeneous matrix equation Ax equals to 0, and we write that as null of A in this way. So let's look at this example. Suppose that A is given by 2 by 3 matrix and U is a vector in R3. Then how do we check U is an element of the null space? Well, basically by definition, the null space is a set of solutions for this homogeneous equation. So we have to check whether we get 0 when you multiply by the matrix A. So in this case, so if you multiply A into U, that gives you 5, 3, and negative 2. And this equals to 5 minus 9 plus 4, and I guess negative 25 plus 27 minus 2, and you get zeros for each entries. So from here, we can tell that the vector U is an element of the null space of the given matrix A. Theorem 5 states that the null space of n by n matrix is a subspace of Rn. So here you have to note that this n corresponds to the number of columns here. So let's check why this has to be true. So recall that the definition for the subspace is given by H is a subspace of V if this satisfies the following three conditions. So first of all, H should contain the 0 element of the vector space V. So for the 0 vector in V, that 0 should be an element of H. And second, H should be closed under addition, which means if you take two elements from H, then U plus V is again an element of H. And lastly, H has to be closed under scalar multiplication. So for any U inside H and C, a number, then if you multiply C into U, then this has to be an element of H as well. So let's check the null space of A, or the set of all solutions for the homogeneous equation satisfies the following three conditions. So first of all, 0 is an element of the null space of A, and this is because, well, if you multiply A into 0, then we know that the result has to be 0 vector as well. And this means that the 0 vector is also a solution set for the homogeneous equation, or the 0 is an element of the null space of A. And for part B, if you take any two elements from the null space of A, then this tells you, well, U and V's are the solutions for these homogeneous equations. And from here, we can tell that, well, A times U plus V equals to AU plus AV, but eventually you get 0 plus 0, which equals to 0. Or in other words, U plus V is again a solution for the homogeneous equation. Lastly, for the scalar multiplication, well, if U is an element of the null space of A, then A times CU, well, we can factor out the scalar outside of the parenthesis. That gives you C times AU, or that gives you C times 0, or this equals to 0 vector. So for this reason, C times U is again a solution, or equivalently, it is an element of the null space of A. Solving the homogeneous matrix equation Ax equal to 0 gives us an explicit description of the null space of A, or in other words, we can find the spanning set for the null space of A. So let's look at the following example. So suppose that A is given by 2 by 5 matrix like this, then the general solution for the homogeneous equation Ax equal to 0 can be found when you find the reduced row echelon form of A. So here, if you multiply -2 from the first row, and then you add that to the second row, then this gives you A is row equivalent to, I guess, 3, 6, 6, 3, and 9, and 0, 0, 1, -6, and -15. And then if you divide by 3 for the first row, then that gives you a reduced echelon form for the given matrix. So from here, we can tell that pivot columns are the first and the third one. So x1 and x3s are basic variables, and the rest are the free variables. So here, we can tell that, well, x3 equals to 6x4 plus 15x5, and x4 and x5s are free variables, and x2 is free as well, and x1 equals to -2 x2 minus 2 x3 minus x4 minus 3x5, or this equals to -2 x2 minus 13 x4 minus 33 x5 when you plug x3 into x1. So from here, we can write the solution set x to be -2 x2 minus 13 x4 minus 33 x5, and x2, 6 x4 plus 15 x5, and x4 and x5. And if you separate each variables, then we get x2 times -2, 1, 0, 0, 0, plus x4, I guess -13, 0, 6, 1, and 0, plus x5, -33, 0, 15, and 0, and 1. So if I let this to be u, and that to be v, and the last one to be w, then we can write all the solutions for the homogeneous equation as a linear combinations of u, v, and w. So we can tell that, well, the null space of A is in fact the span of u and v and w. And we know that span of something always forms a vector subspace of the original space R5. So here are some facts about the vectors u, v, and w's. So first of all, the spanning set of the null space is automatically linearly independent, and this is because, so to check whether the given set is linearly independent, then we have to verify whether this vector equation, say x4 v plus x5 w equal to 0, has only the trivial solutions. But note that this was in fact a different representation for the solution x above, right? Because the way we got the vector equation is we just separated the variables for x. So this is equivalent to have x equals to 0, or this means that x2 and x4 and x5s has to be 0 as well. And because of this, the number of vectors in the spanning set of the null space of the given matrix A equals to the number of free variables of the given homogeneous matrix equation Ax equals to 0. The column space of m by n matrix A is simply the collection of all the columns of the given matrix. So the column space is defined by the span of its column vectors, or the space is consisting of all the linear combinations of the columns of A. Then we know that the column space is also a subspace of R to the m, and this is because the column space is given by a span of a set of vectors. And from the previous section, we proved that span of something is always a subspace of the original space. And note that the exponent for R corresponds to the number of rows of the given matrix A, and this is because the column vector has m entries. So let us find the matrix A such that W is given by a set of vectors of the form in this way. So the goal should be we want to find a spanning set for W, say U and V's, and then we're going to build A by using U and V as a column vector. So we can find the spanning set by separating the variables. The general element for W is given by x1 minus 2x2, 3x2, x1 plus x2, or this equals to, I guess, x1 times 1, 0, 1 plus x2 times negative 2, 3, and 1. So if I let this to be U and that one to be V, then we get A equals to U and V, which is 1, 0, 1, and negative 2, 3, and 1. So here, note that the column space of A gives you the range of the linear transformation, sending x to AX. And this is because we have A times E1 equals to the first column, which is U, and A times E2, which is the second column, that equals to V. So if you write AX to be A times x1 E1 plus x2 E2, then this gives you x1 times the vector U plus x2 times the vector V. So basically, all the elements in the range of this transformation can be written as the linear combinations of U and V, or equivalently, they are exactly the same as the column space of A. And second, the column space of an m by n matrix A is everything if and only if so we know that the range is everything if and only if A is onto, but that is equivalent to say the given matrix equation AX equals to B has a solution for each B in Rn. So let's compare the null space with column space. So suppose that A is given by this matrix, and suppose also that the RREF of this matrix equals to 1, 2, 0, 0, 0, 1, and the rest are zeros. So let's pause the video and try out part A through part B of this example. Okay, so let's solve these problems together. So here, the column space corresponds to the range of the given matrix. So this K corresponds to the number of rows for your matrix. So K should equal to 4 in this case. And the null space sits inside the domain of this matrix. So this K corresponds to the number of columns for your matrix. And in this case, that equals to 3. Okay, so do you see any non-zero vector in the column space of A? Well, I think so. For example, 1, 2, 3, and 0 is one non-zero vector in the column space of A. Then how about the null space of A? Or how do we find the vector in null space of A? So basically, we have to find the spanning set for the null space, or equivalently, we have to find the solution set for the homogeneous equation AX equals to 0. And we can find that by using the reduced form of the given matrix. So from here, x1 equals to negative 2x2, and x2 is the free variable, and x3 equals to 0. So from there, we get x equals to x1, x2, and x3. But if you plug that into here, then you get negative 2x2, x2, and 0. Or we get x2 times negative 2, 1, and 0. So we can conclude that the null space of A is a span of a single vector given by negative 2, 1, and 0. In this case, we can tell that, well, this vector is a non-zero vector in the null space of A. Okay, so let's compare and contrast the null space and the column space of A. So suppose that A is given by M by N matrix. Then we know that the null space of A is a subspace of Rn, but the column space of A is a subspace of Rm. And to find the null space, we have to solve for the equation. It is given by in an implicit way, or we have to solve for the homogeneous equation, Ax equals to 0. But the column space is very explicit, because you can just take the columns of the given matrix. So to solve for the homogeneous equation, we have to apply the row operations on this matrix. We're simply a coefficient matrix, but vectors of column space are linear combination of the columns of A. Well, there's no clear relation between the null space and the entries of A, but indeed each column of A forms the column space of A. And the vector in the null space has a property that A times U equals to 0. And the vector in the column space has a property that, so if you take V inside the column space of A, then we can find at least one X that satisfies this equation. Or this equation has at least one solution, because column space is the range of the given matrix. And for the given specific vector V, we can easily determine whether the vector sits inside the null space by calculating A times V. If that is 0, then it's an element of the null space, and if not, it's not. But for column space, we have to do row operations on the augmented matrix A, V to see whether the given vector is an element of the column space. And the null space consists of the 0 vector if and only if Ax equal to 0 has only the trivial solution. And the column space is everything if and only if the given matrix equation has a solution for every B in Rm. And lastly, the null space is trivial if and only if the map defined by A is 1-to-1. The column space is everything if and only if the map is onto. And there is a nice connection between null space and the column space, and we will see the connection in the later sections. A linear transformation is a function from vector spaces such that it splits the addition like this, and you can factor out the scalar multiplication outside of the function. And the kernel, or the null space of T, is defined by the solution set for the vector equation given by Tu equals to 0. And the range of T is a set of elements that can be sent from the domain of the given transformation. So let's see one cool example about the linear transformation. So suppose that V is a vector space of real-valued function f defined on the interval from A to B, such that the functions are differentiable and their derivative are continuous. And suppose that W be another vector space consisting of all the continuous function on the interval AB. And let's say D is a map from V to W defined by D of f is given by the derivative of the given function. So how do we check whether the map D is a linear transformation? Well, we have to check whether we can split the addition. So for any differentiable functions, f and g, well, we know that we can separate the derivative into two parts, right? df plus d of g. And also, scalar multiplication doesn't quite do anything on the derivative, so you can factor out c outside of d. So from here, we can tell that D is a linear transformation. Okay, then, how do we find the kernel of D? Well, by definition, kernel is a set of element that satisfies the property that if you apply the function on the element, then you should get the 0 vector. Or equivalently, we have f prime of x equals to 0. And we know that the only function satisfies this property is the constant function, or equivalently, the kernel of D is a set of all constant function. Okay, then how about the range? Well, so range is by definition, f belongs to the range of D if we can find a function g such that g solves this equation. But we know how to construct g in this case. So by the fundamental theorem of calculus, if you define g of x equals to integral from, say, x naught to x f of t dt, then we know that d of g equals to the derivative of g, which is d dx integral over x naught to x of f of t dt. But this indeed equals to f of t. But this indeed the same as f of x. So we can tell that the range of this function d is in fact the whole space W, which is a set of continuous function.